Hi, this is Chris Cantalupo. I'm presenting tutorial 3 here from the GeoPM tutorial series. In today's tutorial, we're going to be talking about how GeoPM can use energy policy to adjust runtimes of a imbalanced application in the face of a power bound. So um, let's quickly look through the README and look at the description. This is in the tutorial subdirectory of tutorial 3. It's here. So you can follow along here and we'll talk about uh, this section. So first let's look at, well, actually before we get going, let's start this running because it takes a bit of time. Uh, as before, we're exporting our MPI run or MPI exec environment variable as follows. I've changed the mask a bit here. Here we have this, it has one processor available for the control algorithm, and then we've partitioned 15 different processors for each of the application ranks, and we're running here on 2 nodes. Okay, and so when we run, we're running with 15 OpenMP threads here, and this is our MPI exec as defined above, and we'll be running tutorial 3 today. Um, uh, with 10 total MPI ranks, 4 application ranks on each node. Okay, so let's take a look at the code that we're running. Tutorial 3 has some similarities to tutorial 2, but we have removed all but the dgem region from the loop. And we have modified the size of the problem that will be executed based on the rank. So the first half of the ranks will be running a 10% larger dgem than the second half of the ranks. Because we're distributing these here so that sequential ranks are on the same node, this means that the first node, Mr. Fusion 1, is going to have 10% more work to do in its dgem. We've also made another modification here. We're calling this tutorial dgem static as opposed to the tutorial dgem region. And this differs in that it does the setup of the memory and the values in matrices once, and then stores that in static memory so that each time through the loop, the region is focused exclusively on executing the dgem section of the call. And so uh, what we see is that this is running much faster, but it's also doing 500 iterations. Note that we have a big O principally of 8.0. So um, that's larger than the previous by a factor of 8. Okay, so let's look really quickly at that region code. It's located here in the tutorial region.c right here. And you'll see that the setup here is only done in the case when the big O that comes into the function doesn't match the last recorded big O through the last time this function was called. In that case, you may do some deallocation, reallocation, setup. But in all other cases, well, we're just doing dgem. So in this application itself, we're just going to call through this initialization the first time through the loop, and then we'll call dgem here. And you notice at the end we call the application with the size 0, which deallocates memory. Okay, so now that the app is just completing here, we can take a look at the well, first let's look at the tutorial source, tutorial script source. So cat tutorial 3.sh, and you'll see that this script is actually running twice. So the first time through, it runs with the GeoPM policy, this new variable that hasn't been used in our previous tutorials. And it points to this JSON file, the tutorial governed policy. And we'll take a look at what's in there in just a moment. But note that the tutorial 3 application is run a second time, and this time we've set the environment variable GOPM policy to use the balanced policy. So let's take a look at what's in those JSON files. And you'll see in the governed JSON file, the mode is set to dynamic, and that allows us some freedom in terms of these particular parameters. We're using a tree decider that's the static policy decider, and this basically doesn't adjust the budget as it goes down the hierarchical tree. However, at the leaf, we're adjusting policy according to this power governing decider. And this plugin will keep the node, well, at least the RAPL domains, within the budget that's specified here, 150 watts. Okay, and note we're using a RAPL platform here. So this policy file can be made with the GOPM policy application. There's a minor issue currently on GitHub about that, but this is a proper file. And we can look at the balanced policy. We'll see that this differs in that the mode is set to perf balance dynamic, and you can look in the man page for GOPM policy to figure out the details here about how that's run. And here at the tree level, we're using the power balancing decision algorithm. And again, at the leaf, we're using the power governing algorithm to keep the nodes on average within this 150 watt budget. Each individual node may go above or below the budget, but in aggregate, on average, we want 150 watts per node. Okay, so when we use those two different policy files, we should see different results in our output. So if we look first at the outer sink sections of the tutorial 3 report. So this shows us the output from Mr. Fusion 1 and Mr. Fusion 2. For first, let's look at the governed run. This is using the policy which kept the nodes strictly within the 150 watt bound. And you can see here that because we had injected a load imbalance, in particular the Mr. Fusion 1 has more work to do, you can see that the runtime here is, well, larger than here where we've done the balancing. Here we're seeing a speed up of, well, about 4.5 seconds, a moderate speed up here at the 150 watt bound on the system. And if we look at the time spent in dgem for this same call, so we'll see that in the case where we run the governing decider, the dgem section takes about 133 seconds on Mr. Fusion 1, where we've given more work. But on Mr. Fusion 2, where it has less work to do, it's running just for 117 seconds. But because we have a blocking synchronization in there, we are left with the higher of these two numbers in terms of the cost to the application. Now here, in the balance section, we see that although on Mr. Fusion 2, we've increased the runtime, we've also decreased the runtime on Mr. Fusion 1 to balance out the performance within that power bound. So we see a net win because at the end, this number here, the higher of these two, is the cost of the application for executing the dgem between the barriers. And if we want to look at the trace, here this is the trace from the balanced policy here on Mr. Fusion 1. And we're using awk to pull off the 15th column. And that's where the budget that GOPM is enforcing on Mr. Fusion 1, this node, is located. We're piping that to unique C. And this tells us how many times the sample occurred here in this first column with that value. So the budget stated 150 watts for the first about 1900 samples. And then for Mr. Fusion 1, where there was more work to do, we see that the budget is allocated higher and increasingly higher as it tries to adjust until finally it lands here at 163 watts, and it stays at that budget. If we look at the same output from Mr. Fusion 2, where there was less work, we'll see that similarly, the budget was decreased on this system until it bottomed out at 136 watts and stayed there. So eventually it settled on this budget, 163 watts for node 1 and 136 watts for node 2. And that by balancing the power, we have balanced the performance. Okay, well, join us next time. We'll be discussing a similar problem where we'll be injecting load imbalance by a call to sleep rather than through changing the problem size as we did in this tutorial. Thanks, and we'll see you next time.